Okay, two important dates that we talked about in class that you guys will have missed out on. May 8th is the day that we'll plan on going over to Bonner, and we spend the whole day with the first graders building rockets with them and launching them. And then May 22nd is our Valley Fair Day, and you guys know about that one already. The Bonner Day is, I urge you to do it. It's a ton of fun, but if you have really, really pressing work here at school, well, you can just stay here at school then, and that's fine. But it is a good day.
Tell them they meet us there. Kids will cry.
It's a great day!
Hey, it's a great day to be alive.
It's a great day to be alive.
All right, then. So it has been determined in my brief experiment that I cannot sufficiently coil regular household wire to make a good enough solenoid for this last lab. So we are going to skip lab E, echo. But the rest of them can be done, and since the last lab didn't turn out great either, we don't need to finish those last two because there's no real way that we can use our data to fill in those conclusions. So if you plot out your data and get the formulas, that will be good for the check for that one. Please also remember, lab C is due.
Today?
So get that in. Today would be nice. I'm not going to read them tonight though, but if you've got them, yeah, turn them in later today. Yeah, so if you've got it, it should be like written out, right? And if you've got that all in your sheet, you can bring it up here. But if it's just like a bulleted list, take some time to write it out and then hand that in. And today, then we are going to look at the summary of, had everything gone right on lab D and E, here is what we would have found, sort of deal. And what we're mostly interested in here is different ways to look at magnetic fields, magnetic field strength from different wires, and also then how that interacts with wires. So the ones that we are most interested in are going to be a straight wire, a long straight wire, which ours didn't work out perfectly, and coils of wire. Because both of those are easy enough to build, and we can certainly, we can make measurements. They just don't always turn out quite as well as we want. I want to start, though, kind of tying this together with what we had looked at before, because we have already looked at how much force is applied to a charge moving in a magnetic field, which is at QV cross B is how we'd read that. The velocity and magnetic field are both vectors, and then we also said we can find the magnitude for that by, instead of using this cross product, which if you take upper level math, you'll learn how to do the vector magic with it. But for us, we can just multiply that by the sine of theta to find the value of it. Yeah?
So in math, we're doing like force, or like work. And,
yep. And you're doing a scalar product with those dot products.
We're doing dot product.
But, so we just did, like, the kids who are in physics just did force times distance times cosine of theta, and it worked. But she said it doesn't always work. Like,
I would be very interested to know when it doesn't.
because so we end up doing like the two.
She's like, well, you have an application time.
We did like the two components and then multiplied them and stuff. So when would it not work?
I can't think of a time. But understand that physicists are really, we're not math purists. We use math as a tool, and mathematicians tend to revere the mathematics. And like the math is the thing. And the physicists are like, all right, but I can do this with it. And mathematicians are like, you can't do that! But it works every time. Every single time.
But like given your knowledge of math and stuff, you think it should work?
As far as I am aware, yes.
So then we could just do it to get the right answer and write it down and work together.
You know, Ms. Case, you better do it right if you want all the points. You better do it the math way if you want all the points.
Mr. Sonic told me so.
I want to see this
Discussion.
discussion.
Gonna get a knock at the door tomorrow. 7:30.
No, but if, in all honesty, if she does have an example of when this would not work, love to see it.
Let's go ask her now.
I'll put QED in my paper and see Mr. Sonic told me.
Same thing goes with this, except we have to use the right-hand rule then to figure out the direction that this would be pointing. That's what you get when you're doing the cross product actually with the vectors. You will get the direction coming right out of it. Actually, you'd get the three components, x, y, z, of that vector, and then you could put them together to find to find the total. But for us, we're going to do this and then use the right-hand rule. But there's an interesting application of this because most of the time in real-world applications, we don't have these free charges floating around. We would in, say, a television, in an old-style tube television. Not too many other places, though. Most of the time, our currents are confined to wires. And so it's useful to look at what would this be if we looked at a wire. And so to help us get there, let's look at the units that are involved here. What are the units of Q? Coulombs. How about velocity?
Meters per second.
That's cute.
Okay, B is Tesla. Now, I'm going to rearrange these a little. You've seen me do this once or twice before. What is coulombs per second? Not joules. Amps. That's amps. That's a current.
That's why I didn't get that right.
So that could be a current. What do we use to measure meters?
Distance.
It's a distance. Or length. So if we had a wire, this would be the length of the wire. And B is the same. So a way to write this force from on a wire would be here. Force on a current carrying wire. In a magnetic field, which we usually just say in a B field. Yes? L is the length of the wire. So I'm going to summarize that down here. I is the current through the wire. L is the length of the wire. And that's in meters, of course. So here's in amps. And then V is our magnetic field strength. And in SI, that's measured in teslas.
What is the what is that between?
Still going to be the same as before. So between the current and the magnetic field.
Okay.
So it's still a motion of charge. So you would do the right-hand rule the exact same way. And notice that when we were doing the right-hand rule, we were saying FBI, and I was the current. That's the direction of motion of charge. So same deal with this. We were already sort of using this. Bueno?
No. Sí.
Yeah, alles Gute.
Muy bueno.
Okay.
Mi profesor.
Okay, then there are a couple of different applications that I want to talk about for creating the magnetic fields. First is going to be a very long straight wire. This is one that would have come out of that Biosavar lab had it worked better. And again, your data looked good. nice curves and everything. It seemed to, a lot of them seem to fit. I am at a loss at the moment for why I haven't been able to get that perfect. Well, let's say we got a proportion that said, are we all right? All good? Okay. We had a proportion that said that as we got a very long wire, this magnetic field strength would have been proportional to 1 over r. If it got very, very short, that went to 1 over r squared. That's what we had hoped to find and what the published values showed us. Not so much what we had found. What's that?
Do we believe the published values?
I believe them. I'm not 100% sure if they got them. There's always some doubt with this. Like, my measurement was so bad using your method. How did you get this? Other than you knew what it should have been. Uh-huh.
What's on it?
R is the distance from the wire. And I'm going to summarize that. So this is not the formula. I'm going to summarize it once we get the whole formula. What we could have found from that lab was this, supposedly at least, was this relationship. If we had very, very careful measurements and everything, what we would actually find was that it's equal to a constant, which is abbreviated mu naught, and we'll get to what that means in just a second.
Sound like you said knots.
What?
You said knots again. It sounded like you said knots. So he's like knots again.
I think I have PTSD.
Oh, he said that. Oh, okay. I didn't say that. Over 2 pi times the radius. That's a pi. Okay, so now mu here is a special constant that keeps coming up. It's called the permeability of free space.
So this is the equation, or just mu?
This is mu, sorry. Mu naught. This is something that appears whenever you're doing work with electricity or magnetism, or magnetism in particular, but when you're going back and forth with magnetism and electricity. It's a measured value that we say our universe is built with this value. Yeah.
What does permeability mean?
Sort of like ability. Good. Yeah. It's like a permeable layer is it's like a cell membrane that allows water or sugar to go through it. And so that's a good explanation. How well free space, a vacuum, allows magnetism to go through it. Very good question. And its value is measured. It is 1.26 times 10, and I never remembered this one, times to the negative 6 units of Tesla meters per amp. This is a measured value. I don't know if it can be derived from what we've learned about sort of the basic makeup of the universe or not, but it figures heavily into those calculations. We can measure it because of this relationship. We can measure it very accurately.
How do we get the units?
Ah, well, what are the units of magnetic field? Tesla. So we're multiplying by current and dividing by distance, so if we want Teslas out, that's what it's got to be. I here, of course, is current. In amps. And R is the distance from the wire. In meters. This is a radial distance. This only works for very, very long wires. Think infinitely long for our purposes. In a real life application, it wouldn't be quite that. So this would be R to the 1.05 or something like that. But we're only considering a simple case. For an extremely long wire, this is what it's going to work out to be. Yep, Krista.
So this is measuring a magnetic field from a straight wire.
magnetic field from a long straight wire. If you're a distance away from it of R, and you know the current, then you can find out what the field is around it. We already know the direction because of the right-hand rule. We figured that out pretty quickly. The amount is much tougher to measure.
So, is it R because the thing goes around it in a circle? It's like a radius?
Yep, it's a radial distance from that wire in any direction. We'd have to use the right-hand rule to figure out the direction of this magnetic field. But the value would be the same anywhere around it at the same distance away from the wire. And then there was two others, actually, because we also saw then, if we took and we looped this wire, the magnetic field gets a lot stronger on the inside of it because all of this is adding up on the inside.
So
Yeah.
is it R or R hat?
That would start out.
Actually, it's not R hat anymore because it's at a right angle to R hat. It's perpendicular to R hat.
It's R negative.
So, another thing to look at is magnetic field from some loops. Circular loop. Yep. So we can do, let's do magnetic field in the middle of n number of loops. I have to say of loops. So now if you take that wire and you start coiling it in a loop, we know that it gets a lot stronger going straight through the middle. And from the, of course you could measure this, but you could also use calculus, which we won't. And we would find this relationship. N here is the number of loops. And we kind of know this. We know this from our experiment with when we were coiling it up around a magnetic or an iron core. The more loops we have, the stronger the magnetic field. And hopefully you also found that was, ideally we would find that that's a linear relationship as it is here, but we don't always get that depending on how well each measurement goes. So that's the number of loops that we've got.
Is this what we were supposed to find from our labs?
Ideally, yes. Not so much this one because this is loops in kind of almost a plane. So I'll show you an example. But yeah, that would have been swell. If I could find that. Physics is hard.
Look at that. Oh, crap. I don't know how Joe Bensky does it.
I don't know how anything does that.
Something else
It's hard, but for some people, especially myself included, it was a lot of fun to learn these things. Even though I learned a lot about science and how science is done by a lot of failure.
Yay, failure. Many explosions.
Me too.
Yeah, that's actually really important though, because if you're going out into science or going out into engineering, you better get used to failure and dealing with
So
failure.
that means my failures are successes.
If you learn from them, yes, they're not. You know,
I'm succeeding in this class.
Thomas said it.
So technically I succeeded on everything.
Thomas Edison was famous for saying that he had not failed making the light bulb 1,000 times. He had 1,000 chances to learn. I forget the exact quote, but and learning experiences, and that's definitely true. It's more important what you learn from your failure than that you fail. Anyway, this is what I mean by looped wire. So pretty skinny, much shorter this way than it is around. We can use this, but what we were looking at in our labs was a solenoid, which is a relatively long coil of wires, like so. So the wires are looped around and around and around. And
Let's do some tests.
we'll bring those out later. R here, by the way, is the radius of the loops. And as it says, this is only in the middle. Once it gets out around the edges or anywhere but the middle, it gets really some crazy math. And then the last one here is the magnetic field in the center of a solenoid. Solenoids are actually used a lot around us. I always know that when dinner's on the table and I hear this click from the kitchen, we forgot to turn off the oven. That's a solenoid. So a solenoid is one of these long cylinders with loops in it. Very often there would be a magnet or magnetic material in it that could be pushed out if the current goes one way or pulled in if the current goes the other way. So most of our electronics have this kind of connection, including cars have lots of them, and a lot of the, especially things that have a lot of current, like an oven or a crane.
What click though?
Just commenting on an orange crane back there. Yes.
I looked at a thing a long time ago, and they're making like guns out of electromagnets. They'd have like like a couple wires of a solenoid.
Yep.
Then it'd like get attracted to the next one, the next one, the next one. And it builds up speed.
It basically works like like at Valley Fair with the steel venom. That's an inductive thing. I am still hopeful that I might get to this before we need it. This is a ring gun. And so I think I just need a lot more coils on it. But if I do it successfully, it should shoot a metal ring off of it. It's kind of like that.
Doesn't a lot more electricity on the gun.
What's that?
Doesn't use more electricity on the gun.
And so this works fine at 120 volts if everything else is right. And like I say, I only have 2 or 3 layers of wrappings in there, so I'm not sure that that's enough. I just don't want to sink the $325 into the store-bought one that I could get that does the exact same thing. But let's get back to this. Now this is actually a lot simpler. This, I think the best way I've seen, but I'm very interested to see the results from your labs, the best way I've seen so far to find this result with our lab C is to just kind of see how many BBs can I pick up. And well, that's a lot of pressure, because if yours isn't very good. But I'm very interested to see the rest, because I saw some very good ideas with this. This is actually quite a simple one as far as our formulas go. We still use the right-hand rule to find the direction the field is going inside. But here is the formula, where mu naught is that recurring constant, the permeability of free space. N is called the coil density. Move that over a bit. Linear density of coils is what we can call it. Which is a fancy way to say how many coils per meter are there. And then I is the current going through those coils. And again, this is only along the center of the solenoid, because outside that, outside the solenoid, it starts to spread around, and it really changes a lot as you go around, way beyond what we need to do here. Yeah. Okay, and those are the ones we're going to describe with math. What I want to do we've got 12 minutes today, and I think I will stick tomorrow in there too, is let's do that second homework, which is all practice on this stuff. And use your time wisely, because this is a good time to ask questions and get through roadblocks. So this would be homework. Any questions on what we've seen up here first, though? It'll take you a little practice, yeah.